Today, in this video lecture, we will see numerical on shearing stress. Numerical is a symmetrical beam of I section is 200 mm by 400 mm in size. The thickness of flange is 20 mm and wave thickness is 15 mm. The beam carrying uniformly distributed load of 20 kN per meter over entire length. Draw the shear stress distribution diagram over the depth of the section. This is simply supported beam of length L is equal to 8 meter, uniformly distributed load 20 kN per meter, and section of this simply supported beam is this I section. And we have to find shear stress distribution diagram. That means problem statement in this numerical is to find shear stress distribution. So, for solving this numerical, first step is to find position of neutral axis. Denoted as y bar or y. Here denote this as y. Y is equal to, for calculation of position of neutral axis, we use formula a1y1 plus a2y2 plus a3y3 upon a1 plus a2 plus a3. But in this numerical, we don't use this formula. Why we don't use this formula? See, because this section is symmetrical about x-axis. See, upside of this x-axis and downside of this x-axis both are symmetrical. And this section is also symmetrical about vertical axis. Left side of this vertical axis and right side of this vertical axis both are symmetrical. Due to symmetry, we don't use this formula. So, for calculation of position of neutral axis, we know that this total depth of this I section is 20 plus 360 plus 20. This is 400 mm. And to finding this position of neutral axis, we directly divide this 400 mm by 2. 400 divided by 2, that means 200 mm is position of neutral axis. Second step is to find moment of inertia. For finding moment of inertia, here for this I section, first we consider full rectangle. This red line first calculate moment of inertia for that red color rectangle line. So for that red color rectangle line, about this x-axis, moment of inertia is parallel to x side is 200. 200 multiplied by this total depth is 400. 200 multiplied by 400 cube divided by 12. So this moment of inertia is for that red color rectangle line, but our section is I section. So subtract this part, this blue color rectangle, and this another blue color second rectangle. So what is width of this blue color rectangle? For calculation of width of this blue color rectangle, one blue color rectangle, this total width is 200 minus this web thickness 15 mm. 200 minus 15, 185, and divided by 2 is 92.5 mm. This rectangle width is 92.5 and this rectangle width is also 92.5, and depth of that blue color rectangle is 360 mm. And moment of inertia about this yellow x-axis is 92.5 multiplied by this 360 cube divided by 12 minus 92.5 multiplied by 360 cube divided by 12, and these rectangles are two rectangles. Blue color rectangles are two rectangles, that's why here multiply it by 2. So 200 multiplied by 400 cube divided by 12 is 10.67 into 10 raised to 8. And minus 2 into 92.5 into 360 cube divided by 12. 7.19 into 10 raised to 8. So moment of inertia for that I section is 10.67 minus 7.19, 3.48 into 10 raised to 8 mm raised to 4. Our problem statement is to finding shear stresses. So first find shear stress at this junction between web and flange. So for finding shear stress, we use formula tau is equal to SAY upon BI. So tau is equal to shear force multiplied by area multiplied by neutral axis divided by width and moment of inertia. So tau is equal to, here S is for calculation of shear force for that simply supported beam carrying uniformly distributed load. Formula is S is equal to this uniformly distributed load W multiplied by L. WL is concentrated load and divided by 2. W is 20, L is 8 divided by 2. 80 kilonewton is shear force. This S is shear force is 80 into 10 raised to 3 Newton multiplied by AY. First we have to find shear stress at junction. So we consider above junction area, that flange portion area, for calculation of shear stress at junction. Above, that means above junction area is flange area and flange area is 200 multiplied by 20. So right here area is 200 multiplied by 20 and y is also above junction neutral axis from original neutral axis. Original neutral axis is here at a distance of 200 mm from bottom or from top, because section is symmetric about x-axis or y-axis. So 200 mm, and we have to find neutral. We have to find this y is for here. From here to here distance is 200 minus 200 minus 10. It is 190. So this y is 190. Y is this flange portion neutral axis above this junction from this original I section neutral axis, and divided by, put this B as it is and multiply by I, 3.48 into 10 raised to 8. So 80 into 10 raised to 3 multiply by 200 multiply by 20 multiply by 190 divided by 3.48 into 10 raised to 8. 174.71 divided by B. This B is width at junction, and you all know at junction there are two widths. One width is flange width. This flange width is 200 mm and another width is wave width. Wave width is 15 mm. Let us consider flange width B1 200 mm and wave width B2 15 mm. And at junction there are two shear stresses comes. So first shear stress tau 1 is equal to 174.71 upon b1 and this b1 is 200. 0.874. Unit is Newton per mm square. Next find tau 2. Tau 2 is 174.71 upon wave width b2. 174.71 upon wave width is 15 mm. This is 11.647. Now finding shear stress at neutral axis. For finding shear stress at neutral axis, we use same formula. Shear force multiplied by area multiplied by neutral axis distance divided by width multiplied by moment of inertia. So we have this 80 into 10 raised to 3 shear force. Put this AY as it is and divided by B is neutral axis is at center, that means at this wave part, and wave width is 15 mm. 15 and multiply by moment of inertia 3.48 into 10 raised to 8. So tau at neutral axis is equal to 80 into 10 raised to 3 divided by 15 into 3.48 multiplied by 10 raised to 8 is 1.5532 into 10 raised to minus 5. Multiplied by AY. So shear stress at neutral axis, for finding shear stress at neutral axis, this AY is here we find shear stress at neutral axis, and below this portion we have to find neutral axis. Let us consider this wave portion as 1 and this place portion as 2. So A1Y1, area of that wave portion below neutral axis, x axis, and area of that flange portion. You see A1Y1 plus A2Y2. A1 is area for that wave portion below neutral axis, and below neutral axis wave portion is only this much distance, and this distance is this total distance from bottom fiber to neutral axis is 200 mm. That means 200 minus this flange thickness 20, 200 minus 20, 180 mm. This much distance is 180 multiplied by this thickness is 15. So A1 area for that wave portion is 180 multiplied by 15. And Y1 is centroidal distance for that portion. Centroidal distance for that red color rectangle portion is 180 from this neutral axis is 180 divided by 2, 90. Plus again A2 is flange portion area. Flange portion area is this width is 200 multiplied by 20 mm. And Y2 is centroidal distance for that flange portion from this XX neutral axis. That means this much distance. 180 plus 20, 180 plus 10, 190. This is 180 and half of this 20 is 10. 180 plus 10, 190. Therefore this AY is 180 multiplied by 10 multiplied by 90 plus 200 multiplied by 20 multiplied by 190. 1.003 into 10 raised to 6. Put this AY value in this tau Na equation. Tau Na is equal to tau Na is equal to this AY is 1.003 multiplied by 10 raised to 6. So shear stress at neutral axis is 1.532 multiplied by 10 raised to minus 5 multiplied by 1.003 multiplied by 10 raised to 6 is 15.37 Newton per mm square. And in this T section, I section, shear stress at neutral axis is bigger value compared to shear stress at junction values. So our shear stress at neutral axis comes 15.37 and shear stress at junctions come 11.64 and 0.874. So our numerical is correct. This is checkpoint. So we see now diagram, shear stress distribution diagram. So at junction, shear stress 0.875 Newton per mm square here. 11.667 Newton per mm square. Here 15.37 Newton per mm square. And below this neutral axis there is symmetry in I section, so shear stresses are same. Zero point 0.875. Our value is 0.874 or 5, there is equal, and 11.64 is 11.667, there is equal. .64 Newton per mm square, and here also 11.64 Newton per mm square. You see 11.64, 0.874. So this is shear stress distribution diagram. Thank you very much.